Now, of course, this is the matrix version of the linear transformation. You can have the dyadic version of the linear transformation rewritten by plugging these things in a manner that the correspondence between the dyadic form and the matrix form is more clear. So let's do that. Um, so basically, let's call this equation 1. Let's call this equation 2. Call this equation 3, just for sort of future recall. So let's plug equations 2 into 1. So let's write the dyadic version. So L of V, if we plug in 2 into 1, I'm just going to write the final answer. So what we're going to get is Lxx times Ex outer product Ex, Lyx Ey outer product Ey, Lzx Ez outer product Ez, right? So what this is going to look like is essentially Lxx Ex plus Lxy Ex outer product Ey, Lxz. I'm writing this in a different order intentionally, but that's okay because the order doesn't matter. Plus Lxy Ex outer product. Sorry, I guess we've already done that. This should be Lyx plus Lyy Ey outer product Y. And Zx Ez outer product Ex plus Lzy Ez outer product Y plus Lzz Ez outer product Ez. So this would be considered a pure sort of elementary dyadic representation of a general linear transformation that takes you from a vector to another vector. Okay. Well, I guess this is just the dyadic part, the linear transformation part, and then this whole thing operates on V. So this whole thing is basically just the L part. Okay. So and you notice that this is completely analogous to this 3x3 matrix. Essentially, we have these elementary dyads or elementary tensors, just like you have unit vectors. These are sort of the tensor analogs. These are unit tensors in quote unquote these directions, and these are the components of that 2 tensor or order 2 tensor in those elementary sort of basis directions or basis tensors. Okay, so this is the sense in which we've represented this tensor in these bases. Finally, I just wanted to make a remark about the dyad A outer product B. So what is its matrix representation? So this is the of A outer product B. And let's say we want to represent it in some frame 0. And then we have essentially, let's say the matrix representation of A is AX, AY, AZ, and so given this, and the matrix representation of B is this. The matrix representation of this outer product, of course, that's going to be a 3 by 3 matrix, and that's going to be equal to, so recall, this is a 3 cross 1 matrix, and this is a 3 cross 1 matrix. This matrix is basically A, the matrix, B transpose. Okay, so because this will be a 3 cross 1 matrix, and this will be a 1 cross 3 matrix, and so you'll get a 3 cross 3 matrix. Okay, so that's actually the matrix representation of this quantity. That's the 3 by 3 matrix. Okay, and as an aside, if you're interested in the rank of the matrix, it's actually a rank 1 matrix. Right, so for instance, if we take the dyad EX, EZ, or something like that, that's actually, of course, EX, the matrix representation of that would be, say, in some XYZ, in their own coordinate system, it's going to be 1, 0, 0, and EZ is going to be 0, 0, 1. So this one is going to be EX times EZ transpose, and that's going to be equal to, so I guess we are doing this. So we have 1, 0, 0, and then EZ transpose is going to be 0, 0, 1. And if you do a matrix multiplication of that, we're going to get 1 times 0 is 0. We're going to get a whole bunch of zeros, except in the XZ location. So you're going to get basically 0, 0, 1. Then everything else is 0. Okay, it's just the XZ term is non-zero, and that's basically this this dyad. If you had A equals, let's say this is 3, 2, 1, and B was 4, 5, 6, then of course the dyad A outer product B at 0 is going to be 3, 2, 1 times matrix multiplication 4, 5, 6, whatever that comes out to be. Okay, So that's useful if you are ever needing to find the matrix representation of such dyads given the vectors themselves in some coordinate frame.